What's going on, everybody? Welcome back to another MCAT Mondays. Pretty sure you're surprised to see this one after a long hiatus, but you know what? We're here. MCAT Mondays is here to stay, okay? Remember that. We're always here. We're here to make you from this, a baby, into a full-fledged medical student. Not a doctor yet, because you still have to get into medical school and do the whole medical school aspect, which is 10 times harder, but you know, you're halfway there or a quarter of the way there. I'm gonna stop talking. This might discourage any of you, but let's start this. All right. So today's MCAT Mondays is brought to you by a subscriber of mine, part of the fam, Katya. Hi, Katya. If you're watching this, let me know what you think. And if you're not watching this, then I'm pretty sad because you know what? This was the topic, just watch it, man, okay? All right, we're going over batteries, particularly voltaic cells and voltaic galvanic cells, electrolytic cells, and concentration cells. But first, we're going to have to go over the basics, the foundation, before we get into those batteries, all right? If you already know the foundation, it's good for you because, you know the foundation. I don't know what else to say. If you want to just go over the battery scenarios, I'll just put like a time right here. Okay, so first off, we gotta know something about redox reactions, all right? Which is essentially the transfer of electrons. Wow. You know, those little, just goes like an electron from one atom to another. And there are two schools of thought for memorization here. If you're like me, you like the Leo goes grr, which is essentially like you think of a lion and goes like grr, and essentially stands for losing electrons is oxidation and gaining electrons is reduction. Or you could be a normie and choose oil rig. Okay? No, you don't want to do that. Just or maybe you do want to do that because you're a normie, but essentially oxidation is losing and reduction is gaining. Pretty simple stuff. Yeah, then it gets a little bit more I guess confusing because of job security reasons, or at least I think it's job security reasons. You got reducing agent, which might sound like it gets reduced, but no, it's an agent. So it actually gets oxidized, which means it loses electrons. They got you. They got you. And if you that there would be an oxidizing agent, you're correct. Congratulations. If I could give you a cookie, I would. But coronavirus and the pandemic doesn't let me give you cookies anymore. But you know what? Here, I'll just give you a cookie right there. Congratulations. And so yeah, you got those reducing agents, oxidizing agents. And here's like an example of how it works. So we got an equation called, like this equation right here, magnesium plus 2HBr, and then that leads to MgBr2 plus H2. And thing is though, I think you're gonna have to memorize the oxidation reduction tables, but I'll put it in there too. Just know like the basic, because you don't have to memorize specific atoms, right? Because like it's usually a trend. So for halogens, it's usually -1 is the oxidation state, and oxygen is -2. Hydrogen usually by itself is +1, and it's usually when it's like in the normal state, when an atom is in its normal state, like in magnesium's case right here, it's going to be 0. If it's a diatomic gas by its normal state, it's usually going to be 0 as well, as you can see with the hydrogen there. And yeah, and you can actually break this into two half reactions. One is oxidation, one is reduction. Oxidation you see here is magnesium going into magnesium 2 plus and then +2 electrons. And then the reduction is 2 hydrogen ions plus 2 electrons goes into hydrogen gas. And yeah, you can see it's obviously an oxidation and reduction because you're losing 2 electrons in the magnesium case and then you're gaining 2 electrons in the hydrogen case. Wow. Amazing stuff. Isn't chemistry cool, friends? All right. Moving on. Now we're on to reaction potentials. It's pretty cool, right? Reaction potentials. It essentially tells you how favorable a reaction is based off of the reduction, reduction oxidation states. And oh, whoops, I wrote that wrong. It's reduction potential. My bad, my friends. It's reduction potential. And yeah, so you got like E naught, and E naught is greater than 0 is a favorable spontaneous reduction, whereas E naught less than 0 is no bueno. All right, non-spontaneous. And yeah, oxidation state. The oxidation is exactly the opposite of reduction. If that's also might seem intuitive, you probably could have guessed that. If you did, again, you know what? Here's another cookie. Yeah, but here's one thing. These coefficients, if there's coefficients involved, it's not like K equilibrium states and anything like that. If there's a coefficient in these half reactions, don't multiply it. It's the same coefficient. Yeah. Let's move on to the next one. Next one is adding half reactions to get the full-on voltage of a cell. Yeah, so if V is greater than 0, it's going to be spontaneous. V is less than 0, it's non-spontaneous. And again, you just add the half reactions, and boom, bada bing, bada boom, you get the V. These are all important for batteries coming up. Here's an example problem. I'm gonna give you guys like 5 seconds to think about this, with the E naught values of 0.8 for the first half of the equation, and then the platinum half is going to be minus 1.2. And yeah, let me know what you got. I'm gonna be bumping to Lizzo right now. All right, this might have been a trick question if you did not remember what I said 2 seconds ago, that coefficients don't really matter in this. So this value of 0.8 would still stay the same and will be 1.6. And if you add those two together, 0.8 plus minus 1.2, you get minus 0.4. So it's going to be a non-spontaneous reaction. All right? Cool. I guess we're on the same page. Now we're going on to Gibbs free energy. I don't know why, but like every time I see Gibbs free energy, I always think of Gibby from iCarly. I don't know. Maybe it's because their names are pretty similar. But yeah, so Gibbs free energy minus NFE. N is the moles. F is the Faraday's constant, which is like 96,500 seconds times amps per whatever the bottom constant is. I'll put it in there. I'm sorry. Yeah. You're gonna have to remember that constant though, 96,500. Remember the units too, because units always help. Yeah, and it's gonna so since this equation is negative, and you already know that E is less than 0, at least to a spontaneous. This means that delta G is greater than 0 is also going to be non-spontaneous. Yeah, as well. Which also makes sense because endothermic reactions are non-spontaneous, whereas exothermic reactions are spontaneous. That's a throwback. If you watched my later or earlier videos, it'd be pretty cool if you did. I think I covered that. All right, now we're on to the piece de resistance. Galvanic / voltaic cells. We're at this point right here, ladies and gentlemen. We're at batteries right now. All right, you got these spontaneous reactions. This is what a galvanic battery is. It's spontaneous reactions that generate current. Okay, all right, that's how these are. You got this battery right here. You got 2 half reactions in each compartment. Okay, then you got a salt bridge. That's one salty bridge. KBr, all right? And you got an anode and you got cathode, my friends, anode and cathode, all right? One is aluminum in this case, one is gold. And what happens here, my friends, is that the electrons flow from the anode to the cathode. Wild things are happening right now. All right, that's the current. And you know how this current starts off, my friends? You want to know how this current starts off? Actually, it starts off because it's a half reaction. Each of these half reactions lead to a favorable reaction. The electrons go in, pump through current. So that's why it actually starts off. But that leads to a salt bridge perpetuating that, or perpetuating that. Yeah. So what happens here is, as time progresses, you're gonna have a smaller aluminum, a bigger gold, and that's because as the electrons are being moved over to the gold side, though, there's gonna be aluminum ions in the solution, and that's going to be counterbalanced with the bromine. You also have the opposite scenario where there's gold being pulled out of the solution of AuPO4, and that leads to potassium coming through to that side and compensating for the loss in gold by becoming K3PO4. All right, that's as time progresses. Yeah, so cathode is called a cathode because the cations flow to the cathode, which is the potassium ions, and that's vice versa for anodes as well, because the anions go to the anode. All right, and yeah, so because you're going to have ions in there in the solution that need to be compensated, further compensated, you're going to have that salt bridge in there to actually drive this reaction forward as well. That makes sense. If I need to clarify anything, I will let me know. I will. So yeah, you're gonna have these two half reactions: aluminum, aluminum 3 plus 3 electrons, gold 3 plus 3 electrons into gold. Both of those half reactions are 1.67 and 1.50 with a combined voltage, cell voltage of 3.17. As you guys can see, what we learned before applies here. Now you know that it's going to be a spontaneous reaction because it's a positive value. Yeah. And then, again, V is greater than 0 for galvanic cells. V is less than 0 for non-spontaneous electrolytic cells. So that's the main difference between those two. Electrolytic cells, it's non-spontaneous. You're going to need to actually use a battery to drive the current of the reaction. Yeah, pretty cool stuff. Let's move on to galvanics and the sign of electrodes. For the galvanic side, there's cathode, which is positive, anion is negative. And again, since electrolytic is basically the opposite of that, you're gonna have the cathode, which is negative, and an anode, which is positive. All right. Moving on, concentration cells, one of the main 3 batteries. Yeah, so essentially what's here is both the anode and cathode are made up of the same thing. So if you could guess what changes here, it's the concentration of the liquid, of the solution, the electrolytic solution that is in the different compartments. That's what's the main thing. Pretty intuitive because it says concentration there, but you know what? Still pretty difficult to understand conceptually. So stay tuned right now. All right. So in standard conditions, the E naught value is in a 1 molar solution. So in non-standard conditions, it's going to be different concentrations of the cells. Main thing going on here again is that it's a difference in concentration of the electrolytic solutions. Here in this case, we got 0.2 molar iron chloride versus 0.5 molar iron chloride. And what happens here is you're you're going to have to extract more of that iron in order to compensate for the difference in iron concentrations, right? In the anode side. Cathode side, you're going to have the reverse going on. All right? You're going to have to extract, you're going to have to put the iron in there, in that little cathode, to actually make that reaction, reach equilibrium. So here, the electrolytic solution is actually driving the reaction here, right? Anode's getting extracted iron, cathode's getting sucked in iron, or sucking in iron, right? And in order to compensate this further, you need to have a salt bridge here to, make sure that everything is going in the right way. Cations go to the cathode to compensate for the loss in iron, which is being sucked up by the cathode. And the anions are going into the anode because the iron is getting trickled into the electrolytic solution, and it's going to need to have a partner to tango. All right, it's going to need a partner to tango. All right, because these guys don't like to be alone. Yeah. So electrons flow from a higher concentration to a higher concentration side, which eventually reaches equilibrium, and in this case it's 0.35 molar iron chloride on both sides. So as you guys can see here, the salt bridge is mainly used for compensations of the reactions, which helps drive the reaction forward, because all these anions and cations are going to need a partner. All right. In the concentration cells, all right, the differences in concentration between the anode and the cathode drives the reaction. But in the galvanic cells, the fact that it's a spontaneous reaction drives the reaction, because it's spontaneous. Yeah, well, moving on, we're going to go to the last of the big three, which is electrolytic cells. All right, electrolytic cells, like I mentioned previously, it is non-spontaneous reaction, so it's going to need a battery to drive the current, to drive the current. All right, it's pretty inert, it's pretty ineffective by itself, and it needs that external push to start things going, kick things off. And as you can see here, there's a reason to this, because the reduction side, which is magnesium in this case, magnesium 2 plus 2 electrons is equal to magnesium. And the oxidation states 2O2 minus is equal to oxygen plus 4 electrons. As you guys can see, the E naught values of both of them are minus 2.36 and minus 0.6, or the reduction potential of both of them is minus 2.36 and minus 0.6. And if you add them up, it's minus 2.96 for the cell voltage. And that means that it's a non-spontaneous reaction and needs a battery to force electrons to flow from oxygen to magnesium. And yeah, that's the main differences between those three. As a recap, galvanic cells can run on its own because of the spontaneous reaction. That's literally what drives the reaction. Cell concentration cells need a difference in concentrations in electrolytic solutions to drive the reaction. And electrolytic cells, because they're normies, they need a battery. They need an actual battery to run the reaction. So they need an external source. So they're cool in that way. Yeah. So in this case, for electrolytic cells, the oxygen bubbles away, and the magnesium gets pulled out of the solution and forms around the cathode. Reduction here, many people might think that there might be a difference in reduction oxidation sites. Reduction is still at the cathode, oxidation is still at the anode. Electrons are still flowing from anode to cathode, and anions are just going to the anode, cations are going to the cathode. Just the main difference is you need a battery to run this, and the signs of both of the cathode and anode are going to be flipped. So the cathode would be minus in this case, and the anode will be plus sign in this case. That's pretty cool. That's the end of MCAT Monday's batteries. Katya, if you watch through this entire thing, write MCAT Mondays is cool. And if you didn't, I'll know. There you go. I'm going to make another video later on because my boy Ishraq and Katya asked for how to go over passages. So I'll make that. Stay tuned. Thank you guys for watching. MCAT Mondays, we out.